Okay, so for quiz 14.2, I'm going to do things a little bit differently. I wanted to show you how to work with um, integrated rate law data using Microsoft Excel. So instead of my laptop, um, I'm here on my desktop, and we don't have a good camera here, so it's just going to be kind of a screen capture. Anyway, here we have quiz 14.2, and the first question has to do with rate constants and half-lives, and their relationship is given in uh, my notes here, and you can actually access these notes online on Canvas. But you can see right in the middle of the screen, I've highlighted there the relationship that the half-life is equal to the natural log of 2 divided by the rate constant. And if you're wanting to find the rate constant, you could just rearrange it so that the rate constant is equal to the natural log of 2 divided by the half-life. So if we come back here to our integrated rate laws quiz, we can see some radioactive elements with half-lives ranging from thousands of years to just a few hours. And let's solve this first one. So carbon-14 has a half-life of 5,730 years. So I'm going to head over here to Wolfram Alpha, which is just an online calculator that I like to use. And so I'll take the natural log of 2 divided by that half-life of 5,730 years. And this will give me a rate constant in units of inverse years. But sometimes it's nice to compare rate constants using similar units. So you'll notice on the quiz, I have, let's bring the quiz back up here. I've given you the units of inverse seconds. So let's go ahead and convert our years into seconds. So 5,730 years times 365.24 days in a year times 24 hours in a day times 60 minutes in an hour and times 60 seconds in a minute. So all of this here has now just expressed that half-life in terms of seconds. I hit enter, we'll let the calculator do its work, and it looks like our result here is 3.83 times 10 to the negative 12th. That would be in units of inverse seconds. Going back to the PDF, we have cobalt 57. Its rate constant is 2.95 times 10 to the negative 8th seconds. So we can really just replace this with the new rate constant, 2.95 times 10 to the negative 8th. And that's going to give us a answer of 2.35 times 10 to the 7th seconds. And in this case, the half-life, I think it's best to express in whatever units seem most convenient and intuitive. And so if that's in seconds, I'm going to go ahead and divide by 60 seconds to the minute, divide by 60 minutes to the hour, and divide by 24 hours to the day. And that's going to, those should be multiplied, right? Divided by 60 times 24. And that's going to give us now a number that's a little easier to work with mentally, and that is 272 days. So the half-life of cobalt is 272 days. Oh, shoot. You didn't see any of that. Sorry. I'll just leave that screen up there for a second for you to look at it. Natural log of 2 divided by that rate constant. Then we'll divide by 60 seconds to the minute and 60 minutes to the hour, 24 hours to the day. Okay. And back here to technetium-99, it has a half-life of 6 hours, pretty quick. So in a matter of hours, all of your technetium is going to be reacted away. So we'll divide that by 6 hours, and 6 hours times 60 minutes per hour and times 60 seconds per minute. That's going to give us a rate constant in units of inverse seconds. And if we count our zeros here, this is 3.21 times 10 to the negative fifth. We only get 2 sig figs, I guess. 3.2 times 10 to the negative fifth. The next one is polonium. Rate constant of only 3.73 times 10 to the negative third. Be interesting. 0.00373. Looks like we have a half-life of only 186 seconds. So polonium is going to decay very rapidly indeed. And then our last one is tritium. So tritium is an isotope of hydrogen, and it's radioactive on the order of 12.3 years. And tritium is actually, that's like a really convenient half-life for certain applications. So you can find things like watches or compasses that will have their needles and hands illuminated through radioactive element tritium. And so if you buy one of these watches or compasses, then in about 12.3 years, the brightness of the hands will be reduced to about half of their initial brightness, which is a pretty decent longevity for that sort of a product. It's pretty wild. It's not your everyday glow-in-the-dark watch that uses tritium. These are special watches that are you need to look for them in particular, and they're more expensive than your average watch, right? But anyway, I just thought that was interesting. So we're going to take natural log of 2, divide by 12.3 years, and again 365.24 days to the year, 24 hours to the day, 60 minutes to the hour, and 60 seconds to the minute. And this is going to give us a rate constant of 1.79 times 10 to the negative ninth, although it seems to be struggling to get there. Why doesn't it just give us an answer? That is bizarre. Okay, so what if we do this? There we go. I don't know why it was trying to be altogether too clever when I had written it the other way. But here's our answer, 1.79 times 10 to the negative 9. Okay. So our next question, for each order of reaction, will the half-life increase, decrease, or stay constant over the course of the reaction? Let's come back to my notes here, and we can see the half-lives of the different reaction orders. So for first order reaction, the half-life is natural log of 2 over k. That's going to be constant over the course of the reaction. There's nothing in this equation that will change over time. But for the second order kinetics, we have the half-life is equal to 1 over k times the concentration at the beginning of our half-life measurement. And so as the reaction proceeds, the concentration of A will go down, and that means that the half-life will actually increase. It will take longer and longer and longer to reduce the amount by half. And then if we look at 0th order kinetics here, then the half-life is equal to A naught divided by 2K. And as A naught goes down over the course of a reaction, then the half-life will go down over the course of the reaction. So the half-lives for 0th order kinetics get shorter and shorter and shorter and shorter. Okay, and we'll come back here now finally to our final question. Use the data provided by email. It's actually not in the email, I've posted it in the quiz, but anyway, the data to determine the rate constant, overall reaction order, and reaction order with respect to each of the reactants in a reaction of A plus B goes to C. So here is the data. You'll notice we've got 3 different data sets here. We'll look at this first one, and the idea is to try to see which many different options of types of graphs are going to give you a linear response. So I like to first plot A, and in Excel, you'll go here to Insert, and Charts, I like to do the pull-down menu and come right over here. Any one of these scatter charts would be fine, but when you've got a high density of points, I think it makes the most sense to just do a smooth line. And all we're really looking for is this linear, or is there some curvature? And it's obviously curved, so I'm going to go ahead and delete that. That means that we don't have 0th order kinetics. The next thing to do is to look at the natural log of the concentration of A. So I'll say equals ln, opening parenthesis, come over here to my A column, and I can double click here, and that will populate everything down to the end. And I'll select my time, Control Shift right, Control Shift down, and that highlights everything. Now I'll insert that scatter plot. And I don't actually want most of these data series. It's just quickest and easiest I found to make the plot with all of them and delete the ones you don't want. That way you aren't trying to highlight those 2 columns. Anyway, and we see that the natural log of A plot still shows some curvature, so that means we don't have first order kinetics. Now let's take 1 over the concentration of A. Control Shift down and over is the way to highlight a block of data. We'll insert the same sort of chart again, get rid of all of the series that we don't like. So we're left with 1 over the concentration of A. And here we have some curvature that still remains. And so this reaction is not second order overall either. Now, I can tell you that 1 over concentration of A squared would be the integrated rate law for third order kinetics. Hey, that didn't work. Equals 1 divided by A squared. And we didn't cover that in your lecture, and it's not anything that you necessarily need to know. But because we're gonna sort out the reaction order with those other data sets a little bit later. But we can go ahead and look at this 1 over A squared. Let's insert the chart and get rid of all of this that we don't care about. And you can see that 1 over A squared line now is wonderfully straight. If I right click on it, add a trend line, and I want it to be linear, and I'm going to display the equation on the chart and be done. Let's move it over just a little bit. And that is my 1 over A squared plot. Now, so this isn't zeroth, first, or second order. That is your first key that there's some complexity going on here. And because we have two reactants, we really need to work hard to try and disentangle the effects of them. Is it first order with respect to A and second order with respect to B, second order with respect to A, first order with respect to B, zeroth order with respect to one, and third order with respect to the other? And we're going to do that by these trials. You'll notice this middle data set has 10 times the concentration of B over A, and this final set is the inverse of that. It has 10 times the concentration of A over B. So if we look at the concentration of B over the course of this reaction, oh, my computer's struggling. There we go. You'll notice that it does go down, but not by very much, only by about 10% of its total value, while the concentration of A goes nearly to zero. And so what this does is it means that the concentration of A raised to whatever power it's raised to is going to be constant over the course of this reaction. And we can kind of wrap that into the rate constant. So the rate will equal K prime, some sort of K prime, which is going to be K times B raised to its power times A raised to the M. And K prime is going to equal the true rate constant times B raised to whatever its power is. Right? And so what we're doing here by making sure B remains constant is isolating whatever effect A has in the rate law. So let's, with this set of data, see what's the reaction order with respect to A. Insert the concentration of A with respect to time is definitely not linear. So let's look at the natural log of the concentration of A over time. My bad. Parenthesis. A equals the natural log of A over and down. And we'll insert this chart. And this actually looks really nice and straight. Let's go ahead and let's right-click on there, add a trend line, display the equation on the chart. It always crowds it a little bit too close. I like to be able to see the numbers, and there we have it. Now, we cannot make use of this rate constant just yet. This K prime is equal to 0.0321 times the average concentration of B raised to the power of N. We don't know what that power of N is yet, so we'll come back and we'll revisit it. Now, over here, our last data set shows concentration of A remaining mostly constant, right, and the concentration of B going down to zero. So let's go ahead and graph the concentration of B now against time. Insert chart. And once we get rid of this concentration of A, it's going to adjust itself, and you see that that has definitely got some curvature. So we are not going to be zeroth order with respect to B. The natural log of the concentration of B equals natural log opening parenthesis over enter. propagate that downward. And let's take a look at this curve. Insert, chart. And again, we need to get rid of these others in order to have it zoom in and really show us the shape. Now that looks like it still has some curvature to it. It doesn't look as straight as we would expect from first order kinetics. So maybe we have second order with respect to B. It's going to equal 1 divided by B and let's insert this chart. Insert a scatter plot with smooth lines, and now that looks the way we want it to. That looks like a straight line. Get rid of these others just to clean it up a bit, and add a trend line. So we've got the equation displayed on the chart. Okay, so what does this mean? This all means that we have a third order overall. Here, I'll put it above the column that proved it. Okay, third order overall, first order with respect to A, second order with respect to B. So rate is equal to K, concentration of A, concentration of B squared. What is the value of that rate constant? Well, the most reliable way is to extract it from this line here where we did the integrated rate law for third order kinetics. We didn't really cover that in class, but here the slope is equal to 2 times K. And so it looks like K is equal to something like 6.0. We're probably not justified in more than 2 sig figs there. It'd be something like 6.045. But we didn't talk about third order rate laws, so let's talk about how we could extract the rate constant out of here. K prime is equal to 0.0321, equals 0.0321, and we're going to want to divide that by the average value of B over the course of this reaction. So as long as we have Excel here ready to do all sorts of rapid calculations for us, let's actually find that average value for the column of B. And it needs to be squared because we're second order with respect to B. And that gives me 6.019. Over here we have K prime is equal to K times the concentration of A raised to M. M now we know is equal to 1. So we can do a similar sort of trick here. We'll figure out K is going to be 0.4676. That's the value of K prime. And we'll divide it by the average value of A over the course of this reaction. And we get 6.01. So all of these are actually consistent with each other to within at least 2 sig figs, really about 3 sig figs. The rate constant should be about 6. And if you peek at the code here that is actually generating these data, then 6 is indeed the rate constant that I used. And so that means that, and lastly, the units for K are going to be the units for a third order reaction. So that is inverse molar squared inverse second. So let's take up here our rate constant equation and let's modify it to put an actual value for K. So this would be 6 divided by molar squared seconds times AB squared. So that's maybe a bit of a awkward way to write it here in Excel, but that is the rate equation.